Hello, good day everyone. My name is James, and today we'll be doing a simple revision on topics that we have covered so far. So, you have done revision on units, quantities, measurement, and significant figures. You have also had a chance to go through some more revision in the past few days on other sections which probably were giving you trouble. So for today, our revision will mainly be focused on vectors. So without wasting much time, I'll just get straight to it. The first thing with the vectors, we need to understand when we're dealing with vectors, we're looking at the physical quantities that we have said are measurable. So if you would list among the physical quantities that we have, so of the physical quantities that we can think of, the first that comes to mind would be length. Okay, I'll call it length. You would want to call it distance or displacement, but in that case, we're now specifying what kind of physical quantity this is in terms of whether it's a vector or a scalar. So we have length, which we measure in a standard unit, meters, represented by that symbol. We have mass, the amount of matter in an object, given in kgs. We have time. We can measure that in seconds. What else do we have? We can talk of the basic quantities, would also have temperature. We can talk of current, electric current. So I have 2, 4, 5 so far. So that is 2 more are still missing there. We can measure this one in kelvins, this one in amps. Am I missing an important one? Is there any other unit that you can think of? Mass and length and time, temperature, current. Okay, so let's talk about those in the meantime, right? We have luminous intensity and the more anyway. So those are the other two that make the 7 basic or fundamental quantities. The rest are derived quantities, the likes of acceleration, the likes of voltage. All these quantities, if you think of it, are measurable quantities, right? They are measurable quantities, or we can derive, especially these derived ones, we can derive them from the basic ones, right? Meaning that in this case, like acceleration, it is given in meters per second squared, which is length over time squared. Okay, so there's velocity, an important one, in meters per second. We'll see how different it is from speed, which is basically the magnitude of a velocity there. So, right. Okay. So these are the physical quantities. So when we're saying a vector is a quantity that is fully described by both magnitude and direction, we're looking at any of these vectors, of these quantities, sorry, which have a direction component. So if we are to eliminate in this case, we can think of length is just too broad. So maybe we can go on to say if we talk of distance, then this one is a scalar. If we talk of displacement, okay, it's a scalar quantity. But displacement is distance in a specified direction. That makes it a vector. So already you can see the scalars have to do with the magnitude or the size, which is basically the value in what we have measured, the value of the quantity that we have measured. So the value of the measurement in terms of its quantity or magnitude, as we say, we are looking at the scalar part. So with a vector, there is both the magnitude part, which is what we get from the scalar, but also there is the direction which is given in uh, which is specified or given in a specific direction, right? So, which means with mass, this cannot be a vector because it's magnitude only, time, magnitude only, temperature, magnitude only, current, it's magnitude only, acceleration, vector, voltage, magnitude, velocity, vector, speed, magnitude, which is a scalar. So I've identified my vectors here. I only have three vectors: displacement, acceleration, and velocity. So these are the measurable quantities with which you have already looked at so far, which give sense to measurements or to the quantities of the things that you deal with on a day-to-day basis, whether at home or at school or in any given situation around your environment. Okay. So what is important about these vectors now is to understand what are we doing when we are adding vectors. So addition of vectors or operating on of vectors, operation on vectors is very simple, especially if the vectors are in line. So if A is a vector of magnitude 2, B is a vector of magnitude 1, the two can add to give 2 plus 1, which is 3. Vector C will have a magnitude of 3. They are in the same direction, so they will simply algebraically add to give a resultant with the same direction and greater magnitude. Then if they are in opposite directions, still a vector A, but this is now plus negative B. We get a vector, this time is vector D, which is only a magnitude of 1. So they subtract again algebraically. That's quite simple. The most important thing with vectors comes when we look at vectors that are not in line but are at an angle to each other. Okay, let me continue with the same magnitudes. Vector A, which initially was 2, and vector B, which is 1. And they are linked by an angle between them, which is theta. Okay, so in this case, A plus B, I think I was not doing that here. These are like vectors, so whenever we're adding, we're simply adding that, the vectors. Unless if we are specifically, if we want magnitude of A plus magnitude of B equals to the magnitude of C. So same applies when we deal with, in this case, A minus B, we can say vector A plus vector B equals to vector D. Then their magnitudes, the magnitude of A plus B equals to the magnitude of D. Okay, so in this case, this is different from what's happening in the first one, where even the magnitude of A plus B combined is the same as the magnitude of A and the magnitude of B separately. So you have to be very careful anyway in terms of dealing with these vectors. But most importantly, this, if we are to combine the vectors, then the magnitude of the combined vectors is the magnitude of the resultant. Okay, so this is a special case when this would apply. It's not always. But anyway, what we have here, A plus B, is giving us a resultant, which we can draw here this way. Okay, to give C. So A plus B is giving us a new resultant C. And this resultant C, we have to find it either by using the parallelogram rule, or we could use the graphical method, or we could use the cosine rule for the triangle, right? Because we already know theta, so that is very possible for us to find C. So in this case, if we have vectors of this nature, then what this leads us is to the identification or the resolving of vectors into components, which is also an important thing. So what we would want to do in this case, we have C, which is, let's assume C is horizontal, or even if it's not horizontal, but we need to know what angle is between A and C. What is that angle between vector A and C? So that we can resolve components into the line of action of C. But usually what we would do in most cases is, besides finding that specific angle, we can draw our line. Let me choose blue there and draw the actual horizontal like that. Okay, so now this is the x direction. Then we take all components according to what we have in terms of the angle they make with the horizontal direction. So we'll have an angle there, let's call it phi. We have also an angle there, we'll call it alpha. So in this case, what it means is for components in the x, in the horizontal, so for the horizontal component, which is x, we have ax equals to vector A magnitude cos phi. Then we have bx, which is equal to vector B cos alpha. Okay. So which means for the total components in the x, we've got ax plus bx, which is a cos phi plus b cos alpha. These are the angles each vector is making with the x-axis or with the x direction. So now we can add all components that are in the x in terms of the magnitude of the vector times the cos of the angle between the vector and the direction, the x direction. Same applies vector magnitude and the cos of the angle the vector is making with the x direction. So in the vertical direction, we have the same thing, ay, a as a component in the y, and this component is a sine phi, whereas we also have by, which is minus b sine alpha. Remember, b is below the horizontal and is in the negative direction, so that negative sign becomes important, such that our total vector in the y is a x plus by, which is a sine phi minus b sine alpha. So this is the sum of the components that make the y. That would mean for us to find the magnitude, we'll take x squared. So remember, if these values are known, the phi and the alpha, if these values are known, then which means we have this as the x component and we have this as the y component. And what it will give us are the resultant which is given by the root of, according to the Pythagoras theorem, x squared plus y squared. So once you have that, you can find the resultant as given by the root of x squared plus y squared, such that the angle of this resultant is therefore given by, remember, you have this. So if this is x and you have y there, then you want that angle there, let me call it beta. I have theta already. So tan beta will be equal to, tan is opposite over adjacent, y over x. So the angle there will be, that angle will be arctan y over x. So arctan the value of y, which is what you find after evaluating your y here, given the magnitude of A, which was 1, which was 2, and the magnitude of B, which we said is 1 according to that, then knowing the angles phi and alpha, the angles that each vector is making with the horizontal, we can find x and we can find y. So once we have those, we resolve to the Pythagoras theorem, where we get the resultant and the angle the resultant makes with the horizontal. So that angle, you can see that angle will be this one. This will be the angle beta. That will be the angle beta. So we have found the magnitude and direction of the resultant vector by so doing. So what is important in this case is to note the following. The horizontal component and the given vector do not, or let me say you are given a vector and an angle. You have to be careful. If the angle is between the vector and the horizontal, then that horizontal component is a cos theta component. But if the angle is between the vector and the vertical, then the game is different. You have to really consider the fact that the angle is between the vector and the vertical. Your cos theta component goes to the vertical. So the cos theta component is not always in the horizontal. You have to be careful what is given in the question or what is given in the case that is under consideration. Okay, so let's say we have theta there. We have a vector. This time it's a force, right? So I'll start with it, let me say from an origin. So this is the same force, F, and it makes an angle theta with the horizontal. So now our components are such that, remember, we have let's call this whatever the component will be here, whatever component is down here, it's fx. So, and whatever component is along here, it's fy. So fy is space invariant. Fy can be equivalent to the parallel line that's running at from the head of fx upwards to the end of the vector f, to just complete the vector addition fx plus fy, the components equals to f, the whole force. So these components are the components that are adding as vectors. So they are components of the vector that are adding to give the vector f in full. So f is now like a resultant of its own components. So that's basically what we are doing when we are resolving a vector into components. Okay, so what follows then is the fact that we know that sine theta is opposite over hypotenuse. And in this case, the opposite is fy. The hypotenuse is simply f. So it therefore follows that by multiplying by f both sides, we get fy equals to f sine theta. So already this is fy, and fy is basically the component that is on the other side of the angle that's subtended by uh, the force, which is the vector, and its cos theta component and its other component. So fy is not the one that's subtending the angle. In this case, the sine theta component is always the opposite. So it is opposite to the angle that's subtended, or the angle that you mention in there. So it is on the opposite side. You can want to look at opposite side in terms of the other side of the vector, or opposite side in terms of the opposite of the triangle. Then what it means is, if we were given an angle here, if we had an angle, this angle here, and we call it phi, then it's now different. Fy is now equal to, remember the opposite is now x, and the adjacent is y. So to get fy, we use the adjacent, which is cos phi. So cos phi equals to adjacent over hypotenuse. But the adjacent is fy, and the hypotenuse is f. So you can see that sine theta is equal to cos phi in this case. So that means f cos phi equals to fy. This time fy is a cos theta component. Why? Because, sorry, I'm now calling it cos theta. It's a cos of the angle phi component, because phi is the angle between the component fy and the vector itself. So whenever you are dealing with the cos theta component, your angle theta should be the one between that vector and the component. So it's not always that you have the cos theta component as the horizontal. You should take note of that. It depends on where your angle lies. And the cos theta component is the one between the vector and the immediate component that's subtending that angle. Okay, so let's continue with fx. So when we look at the cos theta in this case, we said it's adjacent of hypotenuse, and the adjacent to theta is fx. So remember, for your triangle, you've got opposite and you have adjacent. So opposite and adjacent. So this is fx over f, and that means fx will be f cos theta, which is what you have always known for the component that lies on the x-axis. So the same applies for phi. In this case, sine phi is adjacent of hypotenuse. Sine phi, sorry, is opposite. No, am I saying adjacent? Opposite of hypotenuse, which is the fx over f. So this leads us to fx equals to f sine phi. That means, in other words, your cos theta equals to sine phi. You know this from your triangles and your geometry, right? So anyway, it in this case, you can see that your fx in terms of the angle there, which is phi, is no longer a cos component, because the angle being considered is with the vertical and not with the horizontal. So that's one thing you have to be careful about, given any situation that deals with these components. Okay, so I'll end there. I'm gonna just pick a few questions that we're gonna do together, and see if we can apply some of these things in terms of knowing the vectors and scalars. One important thing with these quantities, especially when it comes to velocity and speed, yes, with once we have speed in a straight line, then we're mentioning velocity, because a straight line leads to a specified direction. So usually when speed is given and the direction is given as well, then that quantity being referred to is a velocity. An interesting thing happens when we're looking at distance and displacement. With points A and B, the straight line connecting point A to point B is the displacement, whereas the sum of the path traversed in going from A to B adds to what we call a distance. So A and B can be the same points, but when we look at displacement and distance, then we're looking at the straight line joining point A and B being the displacement, whereas the length of the path traversed in moving from A to B gives us the distance. So that is the difference between the two. The distance in this case will be greater than the magnitude of the displacement itself. Yeah. So that means if we would go from A to B and back to A, the distance adds every point of the path taken from A to B and back to A. But the displacement therefore will be equal to, will be 0. So the displacement will be 0 if we go from A to B and back to A. Okay, all right. So let me see if I can find one question. Okay. So we have a person going for a walk and follows the path shown in Fig 3.51. The total trip consists of 4 straight line paths. At the end of the walk, what is the person's resultant displacement measured from the starting point? So we have a starting point given within some x, y Cartesian. Something like that. And it's 100 meters. So the first part there is only 100 meters to the east, and then it goes straight down around 300 meters. That's south. Then makes a 30-degree turn southwest, I would say, for a distance of 150 meters. So 150 meters with a 30-degree angle there. Then a 60-degree turn to the end. Like that for 200 meters. So the question is find the resultant displacement, which is we can call this point starting point A and the end point B. So what we need to do is for this resultant, we need to add all the x components together and add all the b components together and find the resultant. That is the simplest thing we can do. So we can call each part of the motion number 1, number 2. Let me use letters, they're easier. So we start with P, Q, R, and S. So remember, for our resultant, we said we'll deal with the different components separately, such that we'll start with the x component. We should add, this should be equal to px plus qx plus rx plus sx. And the y component, again, py plus qy plus ry plus sy. So now adding these components, or just the x components add together to give the overall or resultant of the x, and the y components add together to give the resultant for the y. Okay, so for our px is 100, qx 0 plus rx. Remember, r has got a component in the negative x direction, and the component in the negative x direction is a cos theta component because the angle is between the vector and the component that we are considering. So we have got r having a magnitude of 150 and it's negative, minus 150 cos 30, the angle is 30 there. Then the same applies. S has got a component in the negative x direction and at an angle of what's that, 60 degrees, at an angle of 60 degrees. So we would take negative 200 cos 60 minus 200 cos 60. So if you wanted, you would still use the positive magnitude of 150, but consider the angle from 0, 90, 180 plus 30 there, it will be 210. So you are probably going to be using cos 210. What does that? Let me see. Yes, cos 210 gives you a negative. So already it autocorrects itself to give you the relevant sign for this. So if you use cos 30, you get root 3 over 2 with the negative there. The negative root 3 over 2 or negative cos 30 is like cos 210. So it depends on how you want to work it out. You just have to be careful and consistent. So now we can add this 100. Just do this here. Okay, so what we have is 100. So I'll just type in 100 on the calculator. 100 plus 1. Okay, that's negative. So negative 150 cos 30. Okay, minus, not there, and minus, okay, 200 cos 60. 200 cos of 60. That's negative 129. So you've got negative 129.9 meters. So this is your x displacement. Overall x displacement is in the negative, and that tallies or agrees with the position of B with respect to A along the x direction. It should be negative. So that makes sense so far. Then for the y, py, you can see the p has no y component, so it's 0 plus, we have a negative anyway there, can already see a negative, negative 300 minus 300 for QY. Then we have a downward component there for R. There's a downward component of RY there. So RY is 150, negative 150 sine 30. So what was I using this? So minus 150 sine 30. Okay. Then the SY is a component that's upward. It's a component that's upward. And it's 200 sine 60. That would be 200 sine 60 plus 200 sine 60. So that's how you can now deal with it to work with the angles that are already given without complicating it any further. So what that means is we have minus 300 minus 150 sine 30. So we can start another one, negative 300 minus 150 sine 30. 150 and sine of 30 and plus 200 plus 2. This one should be negative because it's still below the axis according to the diagram. 200 sine 60 sine of 60 like that, minus 201. So I have minus 201.8 meters, which also agrees. I don't need to check again this working because already B is below the horizontal. So it's okay if it's negative. Now the resultant. Remember, we want to find the resultant of this. Do I have an error? There's an error there. So what do we call it? Displacement. Okay, displacement. So want the displacement there. The displacement is the result of the root of x squared plus y squared. Oh, what is the person's resultant displacement measured from this? So this is not only requesting for the magnitude, so we need magnitude and direction to get a full a description of this displacement. Should be magnitude and direction. So this is the root of minus 129.9 squared plus minus 201.8 squared. So I don't need to put that negative anyway, because once I square it, actually comes off. So don't worry about it. Squared plus, which number is that? 201.8 close bracket and square 239.99. So this is 240 meters. D is equal to 240 meters. And what's the angle? What's the angle there? Remember, arctan y over x. So if we use arctan y over x, we generally are looking for, so this is y, this is x. Tan theta is y over x. So arctan y over x gives us the angle with the horizontal. So angle, direction, so remember we got, let me just go back here. We got x as minus 129. So x was minus, this was the x vector resultant, and the y vector is minus 201.8. This is y. And our angle there is below the horizontal. So we can say theta is arctan y over x. So it gives us that angle there. Arctan 201.8 over 129.9 with their negatives. Where is arctan? Two or 1.8 over negative 129.9, 57.2. So theta proves to be 57.2 degrees, right? So if that angle is 57.2 degrees, it is that angle there. So if we can give it in terms of the x direction, that's 180 plus 57.2. So to the x direction, (180 plus 57.2), which is 237.2. To the x-axis. Or to the x direction, because already we're given the x direction on the diagram. So this can be our reference. It's 237.2 to the x direction. So if you count your 57.2 plus 180 there, you are just going in the opposite direction with a magnitude of 240 meters. So it's 240 to 37.2. That's the resultant displacement. 240 meters. So that's the 240 meters and the angle it makes to the x direction. Okay, so that's quite simple. If you deal with your components, you just do your components right. You know where to use your cos theta and your sin theta for your components. You resolve to find the resultant, and you use the angles to find the direction. So that's basically how you apply this to distances, to forces, whichever way. The vectors, the addition will always be dependent on these components, and make sure you do them right. Okay, I'll just pick one last one, and then we can call it a weekend. So let me see. Okay, that's another one. Let's see if we can get something from this spider, which is making its house. Okay, so in this picture, we can see a spider resting after starting to spin its web. Okay, so the gravitational force on the spider makes it exert a downward force of 0.15 newtons on the junction of the 3 strands of silk. So you can see the vertical strand and the 2 strands that are coming from the upright and the other horizontal poles. The junction is supported by different tension forces in the two strands above it, so that the resultant force on the junction is zero. Ooh, interesting. The two sloping strands are perpendicular, so that makes a 90-degree there between Ty and Tx. And we have chosen the x and y directions to be along them. The tension Tx is 0.127 newtons. Find the tension Ty. Find the angle, the x-axis max with the horizontal. Okay. And the angle, the y-axis max with the horizontal. So tell us what you think, guys. What do you think? How do we start? We need to find the tension Ty. We need to find the tension Ty. The downward force is 0.15 newtons. So already we're given. Let me just draw and hear what you guys think about this question. So this is already 90 degrees. 90 degrees like that. Good. Then this one continues to the end. Then we have the points of contact, like the walls. Then we have a downward force, which were given 0.15 newtons. Then Tx is given 0.127 newtons. We need to find Ty. We need to find Ty. What else are we given? Just the 90 there. Nothing else. Okay. So what do you think? How do we find Ty? How do we find Ty? Any suggestions? So since we're given that the system is in equilibrium, that's the first thing. It means the two tension forces balance up with the weight, right? The two tension forces balance up with the weight, which means the resultant of the two tension forces should be equal to the 0.15 newtons. Okay. So the resultant of Tx squared plus Ty squared should be equal to 0.15 squared. So since Tx is 0.127, Ty squared equals to 0.15 squared minus 0.127 squared. And Ty will be the root of that. The root of 0.006 4, which is 0.08. Ty is 0.08 newtons. Another way to look at it, we can try and confirm this. Let's try and confirm this as well by doing these components. Already we are given its x and y, of course, but we could say yeah, that would be this over 90, that over, we don't know those angles. Okay, I'm sure that's gonna be a long method though, theta, and that makes this angle 90 minus theta. So this will be the same angle, 90 minus theta, making this angle theta. Okay, so what that means is we have 0.127 sine theta. So 0.127 sine theta is upward, plus ty cos theta is upward, should be equal to 0.15. Then the next equation, ty cos theta, ty cos theta, ty cos theta is to the left, should be equal to 0.127 cos, it's ty sine theta here. This is sine, because the theta is on the other side. So it's ty sine cos 90 minus theta, which is sine theta, okay? And 0.127 cos theta. So I just want to verify if the answer we have there is correct. I've created two equations. We have two unknowns. So we can replace sine theta over cos theta. Can we do that? Which one do we eliminate here? So divide everything by sine theta. We have ty equals to 0.127 times cot theta. Okay. And if we divide by sine theta here, we have 0.127 equals that divide by cos theta, 0.127 tan theta plus ty equals to 0.15 over cos theta. So we want to eliminate at least one of the two. Okay, so I see, yeah, this is gonna be a long one. Anyway, the idea with the tricks here will be to square the left side, and the right side we get cos squared, which is sec squared, express sec squared in terms of 1 plus tan squared. Then we have something in tan theta and something in tan theta, both in both equations. But anyway, I don't wanna take that route right now. It's really gonna be a long exercise. But I think the simplest is what we have simply done based on what we information given here, what I've written here in black. We simply know that the system, since it said the resultant here, this statement which says the resultant force on the junction is 0. I think, okay, yeah, that part, which says the resultant force on the junction is 0, it means the system is balanced. So the total downward forces equals to the total upward forces, and the total upward forces are basically the resultant. So what we did is to find the resultant for the x and y, knowing that they are 90 degrees apart. It means we would simply apply the Pythagoras theorem. Okay, so that resultant there will simply be equivalent to the downward force. So that's how we get the ty on that part of the question. But anyway, let's go to the b part so that you can verify this. It should come to ty equals to the same value. I just wanted to verify it that way using the components. So you don't want to use the long methods in most cases. But anyway, B says the angle the x-axis makes with the horizontal. Oh, it's coming back to the same thing. The angle the x-axis makes to the horizontal, which means you have to find theta. Which means we have to find theta. So having found ty as 0.08, we're just doing the reverse of what we're going to do there. So B is about finding theta. So we have ty and we have this. So what do? We say sine theta over cos theta is 0.127 over ty. Okay. So ty sine theta, remember, is to the left. This component to the left is ty sine theta is equal to 0.127 cos theta. Then it means sine theta over cos theta tan theta cross multiply divide by ty cos theta divide by ty cos theta. We remove cos theta there, we remove ty there, we remain with tan theta equals to 0.127 over ty, which is 0.008. That's all, yes. So theta is arctan 0.127 over 0.08, 57.79. That gives you 57.8. That's the angle theta. So the angle, the x-axis max with the horizontal will be 57.8 degrees, and the angle, the y-axis max with the horizontal will be 90 minus that. The y-axis is the one for ty, so the angle it makes with the horizontal will be phi equals to 90 minus 57.8, which is 30.2. 30.2. So let me use these angles to verify my equations again. We are done with this. The angle with is the last one. The angle, the y-axis makes with the horizontal. So that's it with this question. We have the angles. We have the value of ty. So if these equations are okay, we should get the same ty here by substituting that into the equations. So 0,127 times tan theta, 0,127 times tan 57.8. Is it 57.8? Yes. Subtracted from 0,15 over cos theta. So the negative of this plus 0,15 divided by cos 57.8. 0.079. So it gives us ty equals to 0.08. Yes. So yeah, that's it for today. If you want to continue with this one, just out of interest sake, for those that like the mathematics, it's still okay. You could use, let's leave this one as this over tan theta, so that we've got consistency there. Then we go 0.127 tan theta plus ty squared equals to 0,15 over cos theta, and we square. So what we get there is 0,127 squared tan squared theta plus ty squared plus 2 times 0,127 will be 0,254. So that's 0,254 ty tan theta. So that's the product of this and that twice. Then this is equal to 0,15 squared over, or multiplied by sec squared over cos squared, so sec squared theta. Then is sec squared theta equals to 1 plus tan squared theta. You substitute that there. Then already we have said ty is 0.127 over tan theta. So that's another equation that or expression that we use to eliminate ty. Then we remain with an equation in terms of tan theta alone, and we can solve tan theta. So solving tan theta should give us theta equals to this same value, and we can do the same to find ty, having found tan theta. So with theta, ty value will be given there. Or otherwise, there should be another way also for finding ty first without going all the way to the tricks. But otherwise, this is the simplest method. We will get it by just reading between the lines, where we are told that the system is balanced at 0, and having a 90-degree angle between tx and ty means their resultant or the system is in equilibrium. So the resultant of Tx and Ty simply is equal to 0.15, leading to the expression that comes from the Pythagoras theorem. Okay, so I think that's all for today, guys. I hope you enjoyed the session. If you have any questions, please feel free to get in touch with us, reach out to us, let us assist you. If there are sessions from the topics that you have covered so far that you feel you're still behind, we'll be happy to assist you on this channel here on Yebo Physics. Otherwise, from me and everyone here at the studio, enjoy your weekend and happy reading, happy studying. Goodbye.